Have you ever been driving along, maybe cranking your music, and then boom, your headlights dim every time the bass hits hard? Or maybe you're thinking about adding some upgrades to your car, especially if it's a bit older and you're kind of worried about the electrical system keeping up. It's a really common thing a lot of us run into. So today we're doing a deep dive into something called the Big 3 wiring upgrade. We're going to unpack what that actually means, why people recommend it so often, and figure out who really needs it for their car.
It's interesting because while the big three gets talked about a lot in car audio circles, these kinds of electrical things are becoming relevant for, well, pretty much everyone now. Our cars are just turning into, like, PCs on wheels, right? More screens, more sensors, driver assist. It all draws power, so efficient power delivery. Super important.
That's a really good point. And to help us sort through all this, the wires, the volts, the amps, we've dug into a bunch of different sources. Everything from, like, super technical engineering papers to discussions on forums where enthusiasts share what works. Our goal here is really to pull out the key info, the stuff you need to know, whether you're trying to get the best sound or just want your car running right. Okay, so let's get into it. The Big 3 upgrade. For anyone who hasn't heard of it, what exactly are we talking about? Which 3 wires?
Sure. So the big three basically means swapping out or adding to 3 specific, really important wires in your car's electrical system. You use thicker cables, like a larger gauge wire. The first one is the main positive wire. That's the one running from your alternator, which makes the power straight to the positive terminal of your battery. Second, you've got the main negative wire, the ground, that goes from your battery's negative terminal to the car's chassis, the metal frame. And the third one is another negative ground wire, this time connecting the engine block itself also to the chassis. Those are your 3 main power paths. And it's worth mentioning, some people even talk about a big 4.
Oh, okay. What's the 4th one?
They add an extra ground cable running directly from the alternator's mounting bracket back to the negative post on the battery. It just adds, another really solid ground connection, reinforcing how important good grounding is for the whole system.
Okay, that makes sense. So why? Why do we need to upgrade these? What's wrong with the wires the car came with? Why are they a weak link if you add stuff?
Right, that's the core issue. The wiring that comes from the factory, it can be surprisingly thin sometimes. Maybe like 6 gauge, sometimes even 8 or 10, maybe 12 in older cars. It's really only designed to handle the car's stock equipment, the basic lights, radio, engine stuff. That whole system usually tops out around, say, 3 kilowatts of power demand. But then you start adding things. A big amplifier for your stereo, maybe one pulling 1,000 watts RMS or even more, extra off-road lights, winches, you name it. Suddenly, that original wiring, it just can't handle the flow. It becomes a bottleneck.
Right, like trying to push too much water through a small pipe.
Exactly. That's a perfect analogy. Or think of it like this. You wouldn't try to run, like, your whole house's electricity through a tiny little extension cord, would you?
No, definitely not.
Right.
Sounds like a fire hazard.
Precisely. The bigger a wire, the larger gauge, it has much lower electrical resistance. So it allows more current, more electricity to flow easily. It lets your alternator actually deliver the power it's capable of producing without restriction. If the wire's too small, that extra electrical energy just gets turned into heat because of the resistance. It's wasted energy and potentially dangerous heat.
Okay, so upgrading gets you. Better flow, less waste. What are the actual benefits you've noticed?
Well, the big ones are improved conductivity, obviously,
Yeah.
and just a higher current carrying capacity overall. That directly leads to less voltage drop. So less of that annoying headlight dimming when your sound system draws a lot of power suddenly, like on a big bass note.
Ah, the classic dimming headlights.
Exactly. You also get just more efficient current flow throughout the system. This can actually help extend the life of your electronics because they're getting a more stable, consistent voltage. Some people also report, maybe slightly better sound quality, potentially less electrical noise getting into the audio signal. It all adds up to a more stable voltage across the board.
So when should someone think about doing this? Is it only after you install a huge amp?
Ideally, you do it before you add things that draw a lot more power. So yeah, before a high output alternator, before adding a second battery, or even big capacitors. Get the pathways ready first. But it's also just good preventative maintenance, especially on older vehicles. Those original wires, they can get corroded over time, the connections can get dirty, and that adds resistance even if the wire size was okay originally.
Right. But let's be real. Does everyone need this? Is it always the answer? Because you hear debates about it.
Yeah, that's a fair point. It's definitely not a magic cure-all. And here's the key thing. If your alternator isn't actually producing enough power to meet the demand, well, bigger wires aren't going to magically create more electricity.
Okay, so the big three optimizes the delivery, not the source of the power.
Exactly. It lets the alternator do its job efficiently, but it can't make a weak alternator strong. If your lights are still dimming after the big three, your alternator might be the next thing to look at.
Good distinction. And what about newer cars? Do they still need it?
Sometimes not. Newer vehicles, especially ones with bigger engines or maybe just mild audio upgrades, focusing on sound quality rather than just pure loudness, what they call SESC systems, they might actually come with pretty decent wiring from the factory. You might find, say, 2-gauge wire, which is like 35 square millimeters, already in there. That can handle a good amount of current, maybe 200, 250 amps.
Well, how do you know for your car?
Well, you gotta check. Look at the existing wires, see if you can tell the gauge, check the ratings on your main fuses under the hood, and really, really inspect the connections at the battery, the chassis ground, the engine ground. Look for any green or white crusty stuff that's oxidation or just rust. Any of that stuff adds resistance and chokes the power flow. A bad connection or just a wire that's way too small for the power you're trying to pull, like, say, trying to run a 3,000-watt amp through tiny 8-gauge wire that's a serious weak link. It's inefficient, and honestly, it could be dangerous.
Okay, so if you decide, yep, I need this, what kind of wire should you be looking for?
The usual recommendation is a minimum of 4-gauge wire. But honestly, most people doing this seriously tend to go for 2-gauge or even 10-gauge that's 1/0. People often just call it 0-gauge.
Bigger is better, basically.
Pretty much. With electrical wire for power delivery, bigger generally is better. It offers less resistance. And often the price difference between, say, 4-gauge and 2-gauge isn't huge. So many people just go for the bigger stuff for peace of mind. Just make sure you're getting good quality wire. You want oxygen-free copper, OFC. Avoid the stuff called CCA, that's copper-clad aluminum. It looks like copper, but it doesn't conduct as well and isn't as durable for this kind of high current use.
OFC. Got it. And what else do you need? Tools.
Right. You'll need the wire itself, obviously. Good quality battery terminals, the kind with multiple set screw connections, are often easier to work with. You'll need appropriate fuse holders and fuses for the power wires. Then, tools. Wire loom or sleeving to protect the wires. Proper hydraulic crimpers, not just pliers, for making secure connections on those thick lugs. A soldering iron or maybe a small torch can help secure the crimps even better. Heat gun for heat shrink tubing to seal the connections. And then just your basic wrenches, sockets, wire strippers, sandpaper, or wire brush.
Okay, installation. Any key tips? Do you rip out the old wires?
Generally, no. The common advice is to actually leave the factory wires in place and just add the new, larger cables alongside them. You basically piggyback the new wires. More copper is generally better, right? Unless you have absolutely no space, just add to what's there.
Makes sense. And grounding.
Super critical. For all your ground connection points, battery to chassis, engine to chassis, you need clean, bare metal. Scrape or sand off all the paint, dirt, grease, rust. You want that lug making direct, solid contact with the metal chassis or engine block. Bare metal to bare metal, that's key.
And connecting the lugs to the wire.
Best practice is to crimp and solder. Use a good hydraulic crimper to make a strong mechanical connection first, then flow some solder into the connection if you can. That seals it up and improves conductivity. After that, slide heat shrink tubing over the connection and use a heat gun to shrink it down. That protects it from moisture and corrosion.
Okay, crimp, solder, heat shrink. What about fuses? You mentioned fuses.
Yes, very important. You need to fuse the power wires. Specifically, the main power wire running from your alternator to your battery needs a fuse, and that fuse should be rated just slightly above the maximum output amperage of your alternator. And this is crucial. Put that fuse as close to the battery end of the wire as possible, within, say, 18 inches if you can. Why? Because if that wire somehow gets damaged and shorts out to the chassis between the alternator and the fuse will blow and cut the power, preventing a potential fire.
Ah, okay. Safety measure. Fuse near the battery. What about amplifier power wires?
Same principle, really. For any large power wire you run, like to an amplifier in the trunk, you should have a fuse near the battery and potentially another fuse near the amplifier itself, depending on the setup and wire length. Fuse both ends is a good rule of thumb for long runs.
Got it. And routing the wires. Just stuff them anywhere.
Definitely not. You need to be careful where you run these thick wires. Keep them well away from anything that moves steering components, belts, fans, and keep them away from anything that gets really hot, like the engine block itself or the exhaust manifold. Use zip ties or cable clamps to secure the wires neatly every, say, 6 to 12 inches. You don't want them rubbing against sharp edges or flopping around. Now, there's a big but here for modern cars.
Uh-oh. What's that?
Some newer vehicles have these smart sensor boxes right on the negative battery terminal,
Yeah.
or they have complex battery control modules, BCMs, that actively monitor how much current is flowing in and out of the battery. If you just slap your main ground upgrade wire onto the battery terminal, bypassing that sensor, you can totally confuse the car's computer. It might throw error codes, disable charging, or just generally freak out.
Okay, so what do you do then?
In those cases, you might need to connect your main chassis ground upgrade somewhere else on the chassis, not directly to the battery terminal that has the sensor. Or maybe connect it to the body side of the sensor if possible. It gets complicated. If you see one of those sensor boxes on your negative terminal, it's honestly best to do some specific research for your car model, or maybe even consult a professional installer who knows how to handle it.
Good warning. And basic safety, always disconnect the battery, right?
Absolutely. Before you start wrenching on any part of the main electrical system, disconnect the negative battery terminal first. Always negative first off and negative last on when you reconnect.
Okay, so you've done the install, everything looks good. How do you know it worked?
Test it. Get out a digital multimeter, a DMM. Check the voltage at the battery terminals with the car off. Should be around 12.4 to 12.8 volts for a healthy battery. Then start the car. Check the voltage again. Now you're measuring the charging voltage from the alternator. It should be higher, typically somewhere between, say, 13.6 and 14.8 volts, maybe a bit higher right after starting. It should be stable.
What else?
Check your ground connections. Put one probe of the DMM on the negative battery terminal and the other probe on your new chassis ground point and then on the engine block ground point. Set the meter to measure resistance. Ohms. You want that reading to be as low as possible, ideally less than 1 ohm, preferably close to 0. That shows you have a good, solid ground connection. Also, if you have amps, check the voltage at the amps power terminals with the system playing. And check the voltage on the remote turn-on wire terminal at the amp should be, 11 to 14 volts when the radio's on.
Right, and doing this big 3 upgrade can actually solve a lot of common amplifier problems too, can it? Like amps cutting out or going into protect mode?
Oh, absolutely. Insufficient voltage or a poor ground are probably two of the most common reasons why amplifiers misbehave. They go into protect mode to save themselves, or the sound gets distorted, or they just shut off when you turn up the volume. Ensuring you have solid power and ground paths with the big 3 is often the foundational first step to solving those kinds of issues. It makes sure those power-hungry amps are actually getting the clean, stable power they need to work properly.
Okay, so that's optimizing the current 12-volt systems.
Yeah.
But you mentioned things are changing.
Yeah.
The whole system is evolving.
Yeah, exactly. We're kind of hitting a wall with the traditional 12-volt system. It's been the standard for decades, but it's really reaching its practical power limit around that 3 kilowatt mark we mentioned. And at the same time, cars are demanding more power than ever. Stricter fuel economy rules mean manufacturers are looking for efficiency everywhere. Plus, think about all the electronics, bigger infotainment screens, digital dashboards, advanced driver assistance systems, ADS with cameras and radar, and eventually fully autonomous driving systems. It all adds up to a huge power draw that 12 volts struggles to handle efficiently.
So what's the solution they're looking at?
The industry is moving towards a new standard, sometimes referred to by its technical name LV148. It involves adding a secondary higher voltage electrical system, a 48-volt system that works alongside the existing 12-volt system.
Okay, so not replacing 12-volt entirely, but adding 48-volt on top.
Exactly. You typically have a 48-volt lithium-ion battery, often a component called an integrated starter generator, or ISG, which can act as both a powerful starter motor and a generator, and then a crucial piece, a bidirectional DC-DC converter. This converter acts like a bridge, managing power flow between the 12-volt and 48-volt networks. Together, this dual-voltage system can deliver much more power, potentially up to 10 kilowatts combined. That's a big jump from the 3 kBu limit of 12 volts alone.
Wow, okay, 10 kilowatts. What does that extra power enable? What are the benefits?
There are quite a few, actually. First off, fuel economy. For regular internal combustion engine cars, adding a 48V mild hybrid system can improve fuel efficiency by like 10 to 15%, which also means lower CO2 emissions.
How does it do that?
It allows for much smoother and more frequent engine stop-start operation. The 48V ISG can restart the engine almost instantly and seamlessly. It also enables more effective regenerative braking, capturing energy when you slow down and using it to charge that 48-volt battery. And beyond fuel savings, it opens the door for new performance and comfort technologies. Things like electric superchargers or turbos that can spin up instantly using 48V power, giving you boost without waiting for exhaust gases.
Ah, so quicker acceleration, potentially.
Right. Also, active suspension systems that react faster, electric water pumps, electric power steering things that draw significant power can run more efficiently on 48 volts. Another big plus, because power equals voltage times current, PBIVI. If you increase the voltage V, you can deliver the same amount of power, P, with less current. Less current means you can use thinner, lighter wires.
Ah, okay. So it actually helps reduce the amount of heavy copper wiring needed in the car.
Exactly. Which saves weight and cost. Some high-end cars today have like miles of wiring, over 4 kilometers in some cases. A 48V system helps trim that down. And critically, it provides the headroom needed for all the power-hungry components of future autonomous, driving the powerful processing units, the LiDAR sensors, radar cameras, plus all the connectivity features we're starting to expect.
That sounds like a huge shift. Must be a big challenge for the companies making all the cars' electronic parts.
Oh, absolutely. It's a major engineering challenge, especially for semiconductor manufacturers and the makers of all the electronic control units, the ECUs or computers in the car. They have to design components that can safely and reliably handle these higher 48-volt levels, which behave differently than 12 volts. And that's where those bidirectional DC-DC converters become so important. They need to be incredibly efficient and reliable to manage the power flow between the two voltage systems without wasting energy as heat.
Right, and there are specific chips being designed for this, you mentioned.
Yeah, companies like Linear Technology, which is now part of Analog Devices, have developed specialized controllers. One example is the LTC3871. It's designed specifically for these automotive dual voltage systems.
What makes it special?
Well, it's a bidirectional controller. That means it can step the voltage down from 48V to 12V, that's called buck mode, to power the legacy 12V components. But it can also step the voltage up from 12V to 48V, that's boost mode, for example, if you need to charge the 48V battery from the 12V system, or maybe provide extra power during starting. And the really clever part is that it can switch between buck and boost mode on demand using the same set of external power components, inductors, capacitors, MOSFETs. That really simplifies the design for the car manufacturers.
So it's flexible and efficient.
Highly efficient, yeah.
On
Up to
top.
97% efficiency, they claim, which is critical because any wasted energy turns into heat, and managing heat in tightly packed automotive electronics is always a challenge. And it's built tough for cars, meeting those ACQ 100 automotive reliability standards and supporting functional safety requirements like ISO 26262.
You also mentioned it could handle high power.
Right. You can parallel multiple phases of this controller, up to 12 phases, apparently. This allows it to handle really high currents, maybe up to 250 amps, delivering something like 5 kilowatts of power transfer between the batteries. And crucially, it allows both the 12V and 48V batteries to supply power to the loads simultaneously if needed. So if you have a sudden high demand, like when starting the engine or powering an active suspension movement, both batteries can contribute.
Okay, so it's clear that the whole electrical backbone of cars is undergoing a pretty major transformation towards these more complex, higher voltage systems. Understanding power delivery is becoming even more important than ever. So wrapping things up then, whether you're looking at doing a big 3 upgrade on your current car to get your audio system sounding its best and your lights shining bright, or you're just interested in where car technology is heading with these new 48-volt systems, it really all boils down to the same core idea, getting power where it needs to go, efficiently and reliably.
That's exactly right. These upgrades, whether it's the big 3 or the move to 48 volts, aren't just about adding more power randomly. It's about optimizing the pathways for the power your car generates or stores. It's about making sure your alternator isn't being choked off, protecting your expensive electronics with stable voltage, reducing wasted energy, and ultimately just making the whole driving experience better and more reliable.
So thinking about this rapid evolution, all this increasing demand for power, for computing, for sensors, for new features, here's something to ponder. What completely new, maybe even surprising power-hungry features do you think we'll see become standard in cars over the next, say, 5 or 10 years? And how will the car's electrical nervous system have to adapt even further to keep up?